So we're going to be looking at exponential functions, major focus on graphing them. We'll also be looking at growth and decay of exponential functions. We actually see a lot of this, especially right now with coronavirus. It's an exponential growth with disease, an exponential decay with other things as well. So in the name, exponential functions, we do want to review our exponent and exponent rules. The biggest one for exponential functions, exponents mean shorthand for repeated multiplication. So 3 to the third is 3 times 3 times 3. We all know what that is. 10 to the fourth would be 10 times 10 times 10 times 10 4 times. The big one is negative exponents mean repeated division. So 4 to the negative third really becomes 1 over 4 to the third. 1 over 4 times 4 times 4. Meaning if you have anything, 10 to the negative second, that 10 to the second is now on the bottom of the fraction. And if you have nothing else to put there, we put a 1 on top for a placeholder. We did have a few exponent rules to go through, just to review. X to the fifth times x to the fourth, because they're both the same base, and they're multiplying, we can add the powers. That's x to the ninth. Quotient rule, same base, but they're being divided. We subtract top minus the bottom, so this becomes y to the third. And the power rule is kind of like the distributive property. The 4 multiplies the 2, and we get z to the 8th. Alright, so kind of review some of our functions. What kind of functions have we worked with this year? Linear, some of the big things. Constant rate of change. They're straight lines. And they have constant rate of change is also slope. Those are the telltale signs that you have a linear function. Quadratic, what we just kind of got done working with. They are parabolas. They're symmetrical around a central axis. And there is no constant rate of change. So now we're going to look at exponential functions. And exponential functions, they're not linear, they're not quadratic. The variable is actually in the exponent. So this is 10 to the x. So when we plug in our value, so we can kind of compare our functions. Let's say we have, here's linear, quadratic, exponential. We're going to plug in the numbers 0, 1, 2, and 3. Our linear function, let's just say, is y to the 2x. Quadratic is y equals x squared. And exponential is y equals 2 to the x. All using the exact same numbers and variables, just in a different manner. So if we plug in 0, 2 times 0 is 0. We plug in 1 for x, 2 times 1 gives us 2. 2 times 2 gives us 4. 2 times 3 gives us 6. We notice with our linear, everything is moving by a constant value of 2 every single time. And over here would be 1. That's how we get our rate of change, 2 over 1. Doing the same thing for quadratic. We plug in 0. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. We can see that it's growing at a much faster rate, but not constant compared to the linear. For our exponential, we're actually going to put our x value into the exponent. So this is 2 to the 0, which is 1. 2 to the 1, that's 2. 2 to the 2, 4. 2 to the 3 is 8. So we can see that it's growing, it's doubling every single time. as we increase. What's crazy is any exponential will outgrow any other function no matter what. Even though right now we're like, cool, quadratic is more than the exponential when x is 3. But if I were to plug in 10, 10 squared gets us 100, that's cool. But 2 to the 10th, I'm not 100% sure, so let's find out, is 1024. So you can just see how fast an exponential function grows. At 3, the quadratic was just barely more than it. You get to 10, 7 digits away, 7 values here, and it's a 10 time difference. That's just crazy. There are no tips or tricks to graph an exponential. We are going to plug in values and go with it. The best part about exponentials, because they grow so quickly, we don't have to plug in a lot of values. We're going to plug in -2, -1, 0, 1, and 2. We might plug in some other ones if we want to get a better picture. Alright, let's start with the easy one. 0. 2 to the 0, anything to the 0, is 1. So our exponential, when we plug in 0, it's going to spit out 1. We plug in 1. 2 to the first power is 2. So at 1, comma 2. And then 2 to the second power gives us 4. Alright, I don't know if that's enough really. Let's do one more. Let's plug in 3. It spits out 8. If we wanted to do 4, that spits out 16. No, very quickly we aren't able to graph a lot of those points. So 3, 8. 2, 3, 4, 5, 6, 7, 8. I don't know if I'll be able to get 16 on here. 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, technically I could get 16 if I wanted to right there. 4, comma 16. Going the opposite way, we're going to plug in our negative values. We get 2 to the negative first power, which really means 1 over 2 to the first power, which is just 1/2. So over here, -1, 1/2. 2 to the negative second power gives us 1 over 2 to the second power, which gives us 1 to the 1/4. So right there. What ends up happening with an exponential is on one side of it, it grows very, very quickly. It is possible to flip our exponential and have it do this instead. Just not in this particular case. So the other side of an exponential will almost level out. So drawing that same one, this would be the left-hand side of the exponential. It hits right here, and wow, it takes off like a rocket. Probably even steeper than that. Probably like that. Over here, I can't physically draw it well enough because I'm just not coordinated enough. Maybe someone who has better handwriting. This part of the graph will forever continue to get closer and closer and closer to 0, but it will never ever cross. Like if I were to zoom in right here at this section of graph, here's the x-axis in red, and then the graph in purple, it's like getting closer and closer and closer and closer and closer and closer and closer. And then if we were to zoom in, and we'd like keep going out to infinity, like to our graph way over here. I'll draw another picture of that. This is way out at infinity. That graph is still getting closer and closer and closer. Like it's still never going to really touch. It's getting closer and closer and closer and closer every single time. That's called a horizontal asymptote. Horizontal asymptote. It is a line that a function will never cross. Ah. The line exponentials will never cross. Every exponential function has one. Has this horizontal asymptote. Most of the time it is 0, but it can change depending on the exponential function. So let's try one, -3 to the x. Notice that the -3, it's not in parentheses like this. It's a negative and then a 3. Very different. So essentially this one is -1 times 3 to the x, like this. That means I'm going to have to change my graph down here. Because if I'm going to have a negative in front of it, just like what happens with linear functions or with quadratics, it's going to cause this exponential to flip upside down. So let's try a few. Same thing, we're going to plug in 0, 1, and 2, -1, -2 over here. Maybe plug in 3 and 4 if I need to get a better picture. We plug in 0. Alright. Got to be careful, this is why we're going to actually show our work over here. -1 times 3 to the 0. That's -1 times 1. It spits out -1. Already underneath our x-axis. We plug in 1. 3 to the first power gives us -1 times 3, gives us -3. We plug in to the second power, this gives us 9. That gives us -9. 4, 5, 6, 7, 8, 9. The next one, if we were to plug in, if we were to plug in 3, that would give us 27. It would spit out -27, and I'm pretty sure I can't plot that point. It's going to be way down here. So the right-hand side of our exponential function just grows super crazy fast, like this. Or it actually doesn't grow. It's technically not called a decay. This is a negative growth. As weird as that sounds. It's not a decay, it's a negative growth. And yes, there is a difference. Something we're going to talk about on day 2. Today we're mostly focused on plugging in values and plotting them on the graph. So if we were to do the same thing, but this time plugging in our negative exponents, still -1 times 3 to the -1st. That's -1 times, dang it, 1 over 3, so we get -1/3. So on the other side, there's our value. We plug in -2, gives us 1/9, so we get -1/9, so it gets a little bit closer. And here's where we could kind of see empirically why it will never cross 0. That's why it's horizontal asymptote. -3 would be -1/27. If we really want to, -4 becomes -1/81st. You could pick any really large -100. I have no idea what 3 to the 100th power is. Let's see, 3 to the 100th power. 1 divided by that answer. Alright, it would be, if we were to put 3 to the -100th power, it would be 48 zeros. and then a 1 right there. But that's still not 0. Right above 0. And then the negative would make it negative, of course. So we have that horizontal asymptote. Our exponential is never going to cross the x-axis going the other way. So it basically levels out. Best way we can draw it. Maybe our starting value is already a fraction. This is going to cause a decay in an exponential. We're going to plug in the same ones, 0, 1, and 2, negative 1, negative 2. And then the same thing, I'm going to have to change my graph a little bit. I'm going to move my y-axis over a little bit, just a smidge, like this. Alright, so if I plug in 0, once again that's 1. It hasn't changed. Anything to the 0 power is 1. But when I plug in 1, 1/2 to the first power is 1/2. And then 1/2 to the second power is, we square the top one, so it's 1 squared, and then 2 squared. According to our power rule, we get 1/4. The next one we'd get would be 1/8, 1/16, 1/32, 1/64. This would just hover right above our x-axis, but never actually cross or even touch it. Looking at our negatives, we have 1/2 to the negative first power, which means I'm going to flip my fraction and put everything to the first power. So that's just 2. One half to the negative second power. The negative causes the fraction to flip, and then everybody has to be squared. So we get 4 over 1, or just 4. And then the other side, that was not my best, is it's growing super duper quickly. Not my best, because it never becomes perfectly vertical, because if it does, it's not a function anymore. And it just keeps growing super duper crazy all the way up. Again, it's because I have to keep moving the screen. It just keeps messing up my drawing. I'll try one last time, and then I'm just going to call it good regardless. Something like that. Last one we're going to look at for day 1. We have the negative again. It's on the outside, so it's not going to be included in any of the exponent powers. Meaning I get to take this picture once again, and since the negative on the front is going to flip it upside down, I'm going to move my x-axis to top. Move this over just a smidge as well. And let's work on a few of these problems. Again, 0, 1, and 2, negative 1, negative 2. Plug in 0. You've got to be careful. We have the negative 1 times 1/5 to the 0. That's negative 1. Negative 1 times 1/5 to the first is negative 1/5. Negative 1 times 1/5 to the second power gives us negative 1 times 1 over 25, so we get negative 1/25. Even closer. So on this side, it gets closer and closer and closer and closer and closer. Like that. This one we have negative 1 times 1/5 to the negative first power. The negative causes this to flip, and then everybody gets to the first power, so that's just themselves. You get negative 5. We square the next ones for the negative 2, so we get negative 25. Again, I don't know if I'm going to be able to plot negative 25, but that's okay. So negative 1 is 5 right here. The next one will be 25. So you can see just how fast this thing falls like this. So the four major things that we're going to see with exponentials, the four types of graphs, they are possible to be shifted, and that's what we're going to look at on day 2, is what causes these things to move around the graph. So you have this. This is an exponential growth, because as we go from left to right, it's growing. Then we have this. This is an exponential decay. The other way is if it's flipped upside down, it can look like this, or like this. As of right now, I'm not 100% sure which one's growth or decay, because I've been thinking about that for the last couple of minutes. I'm going to look it up and find out. So we have this. So we have our growth, we have our decay. If it gets flipped over, because now it's a negative in front. So if we want to give this one values, this is like 2 to the x. This one becomes 2 to the negative x. This one is negative 2 to the x, while this one is negative 2 to the negative x, right there. And I'm pretty sure this one is still classified as growth, and this one's still classified as decay. I'm going to look that up, and I will make any corrections if I described it wrong, and we're going to talk more about growth and decay as this unit continues. We're going to talk about it more on Wednesday.